In this module, Module 2, Theory of Adhesion, I want to explain you in which conditions we have a good bond between the adhesive and the adherent or substrate we want to join. It's time now to discuss the theory of adhesion. I want to see these things with you and answer the question, in which conditions do we have a good adhesion between the adhesive and the substrate. So, first of all, let's analyze the forces involved and those that will resist separation when you apply a load. You have basically two types of forces. You have the primary forces and the secondary forces, or chemical forces and physical forces. The primary or chemical seldom are present in a joint. You don't have exchange of electrons between the adhesive and the substrate. You have exceptionally if you apply a primer or surface treatment, but in general you don't. What you have are physical forces. Van der Waals forces, for example, very common. And within these physical forces you have of two types. You have the strong ones and you have the weaker ones. The strong ones you can call them polar, and the less strong the dispersive ones. And this has to do with the fact that any atom or molecule, they are not always perfectly symmetrical in terms of charge. There is always one part that is more positively charged than the other part. And this creates forces of attraction. When the asymmetry is permanent, then the attraction is also permanent and stronger. Then you have what is called the polar force. When the asymmetry is only momentaneous and varies with time, then you have dispersive forces which contribute to the forces of attraction but are way weaker than the polar ones. So the ones we really are looking for are the polar ones. And whether they are dispersive or polar, these are present in any type of joint, okay? But all these forces, whether they are primary or secondary, and for the secondary, again, we can call it physical, any of them, they have this in common. They are forces that act in very, very short distances. We are talking about angstrom of the order of 10 to the minus 10 meters, really a very small fraction of micro. And if you look at the roughness of the surface you are going to bond, they will have always a certain roughness. The roughness is in fact 1,000 times the distance of action of the forces involved. So if you want to bond an adhesive that is in the solid state to a substrate that is also in the solid state, then you will have a situation similar to this one. There will not be intimate contact between the two. They will touch, okay, in some for a very small number of points, but it's not enough to create a good bond. You would want this one to match perfectly the substrate so that you have a huge area of contact and therefore high strength, because you would have a lot of physical forces, a lot of Van der Waals forces involved. But that's not possible. If the adhesive is solid, that's not possible. How do you guarantee that the adhesive will match perfectly the substrate? The only way is to apply the adhesive in the liquid state, which is represented here. That's always the first part of the fabrication. Apply the adhesive in the liquid state so that it matches perfectly the substrate and create a lot of physical forces. Good. We are right, we are happy. We spread the adhesive along the substrate, a good intimate contact. The problem is that the liquid has no strength. So if you load a joint where the adhesive is liquid, you will have no strength. That's why, after applying the adhesive in the liquid state, you need to change the phase of the adhesive. You need to change from liquid to solid. So that's the phase change, okay? It's called also hardening or also curing, okay? When it's cured, then you are happy and you have a joint that is very strong because the adhesive is solid. So these steps are really important. Application, the liquid phase, and change of phase, curing, hardening, so that you have a joint strength high enough. The hardening process, or the cure, it's another term used, can be done in three ways. You can have a loss of solvent. This is, for example, the case for the white glue in wood. It can be from the cooling state. That's the case of the hot melts, the thermoplastics. But in general, for structural applications like the adhesive that we see in airplanes, we are talking about a chemical reaction between a resin and a hardener, all right? And this leads to a thermoset adhesive, like an epoxy adhesive. Okay, but does a liquid wet in every situation a solid? I said yes here. I said if it's liquid, we are all right. We will create an intimate contact. But do we have spreading in every case? Not really. You have a nice image here of drops of rain that in fact do not wet the plant. So this is not trivial, and it's not because it's liquid that you will have wetting. It's more complicated than that. And to show you with different substrates, I have here on the table 4 types of substrates, okay, of different conditions. I have glass here, I have metal here, I have a polymer here, and I have cabbage here. All right, cabbage. Cabbage is a material, of course, natural material. Let's start, and I'm going to put a drop of water in the 4, and we are going to see how the water behaves, how the water spreads. All right. Now let's start with the glass. Okay. Nice drop of water. Right? What do you think? Yeah, it spreads quite well. Let's do the same for the metal. Not as good as with the glass. You can see that the glass spreads better. It spreads, but not as good as with the glass. Now let's go to the polymer. It's getting even harder now, okay? So easy, still not bad. It's getting hard. Let's see what happens now with the cabbage. Can you see how beautiful it is? It forms spherical droplets. So you go from easy, still not bad, complicated, impossible, okay? It doesn't wet at all, the surface, which is what you have in the slide, okay? So the idea that if it's liquid, we win. No, it's not as easy as that. You can analyze this in a more scientific way by looking at the contact angle that the drop of liquid forms at the surface of the substrate. This contact angle, theta. And this in fact varies. It varies a lot. It varies from 0 degrees, which is perfect wetting, not far from what we have in glass, to a perfect spherical drop, which is what we have in the cabbage. Of course, the ideal situation is this, but this is ideal, really. It does not happen in practice. If we are at an angle of 90, less than 90, in general it works. With a bit of help, with a bit of pressure, it should work, all right? The contact angle also appears in very, very, very famous equation of Thomas Young, more than 200 years, this equation, which relates the surface energy at this point of the drop, and says that the surface energy of the solid is equal as that of the interface plus that of the liquid projected here with cosinus theta. But what is this, the surface energy? It's a concept that is not that easy to understand. We can understand this by describing the surface energy as the unbalance of attraction forces at the surface. What happens is the following. For the molecules that are inside the liquid, molecules or atoms, they are in a very comfortable state because there is a balance. They are in balance in terms of force in all directions, all right? So very comfortable to be inside. Those that are at the surface, that's another story. There is a force that in fact pulls them down. It's not comfortable to be at the surface. To be at the surface, you need an extra energy. These that are at the surface are in an extra energy. That's that extra energy we are talking about, the surface energy. That's this surface energy, for example, that allows some insects to float at the surface of water, or a clip to float at the surface of water, okay? For solid is less obvious to understand the effect of surface energy, but for liquids, very, very obvious. But what do I do with that surface energy? I can go back here and interpret this more or less in a complex way. Or you can look at this in a very, very simple way and use the principle of minimum energy. And this principle says the following. If you substitute a surface with a high surface energy, that of the solid, with the surface energy, or with a surface that has a low surface energy, which would be the liquid, then the total energy of the system drops, and this is a spontaneous process. In other words, if the surface energy of the liquid is lower than that of the substrate, then we are right, the liquid spreads. If the surface energy of the liquid is higher than that of the substrate, we are in trouble. The liquid does not spread. Okay, but can we predict which substrates will allow the liquid to spread? Yes, in fact we can. This is related to the hardness of the substrate, curiously. The harder it is, the higher will be the surface energy, and the easier will be to bond the substrate. That's why glass, which is a ceramic, is very hard, very easy to bond because the liquid spreads nicely. Metal, not as hard as a ceramic, but still alright. Polymer, they are quite weak in terms of hardness. It's getting very difficult to bond. Cabbage, forget it, very extreme, but we don't bond cabbage, it's another story, alright? But that's, you can make that relation. The stronger the substrate, the easier it is to bond. Polymers in general, very difficult to bond. But what can I do to make things better? Well, those substrates, those materials that by nature have a high surface energy, what do you need to do? You need to clean them before you bond. For example, the aluminum, if it's oily, if it has dust, then you clean that dust, that dirt, and then you are all right. But if I have a polymer, if I clean, no, it will not change anything. You need to do something to the material. You need to apply a surface treatment that will increase the surface energy. All right? Okay, so what I've seen, or what I've shown you so far, it's one of the theories of adhesion, in fact. It's the theory of adsorption that says that if you approximate sufficiently close the molecules of the adhesive to the substrate, then you have the forces, the van der Waals forces in action. And this is sufficient to have a strong joint. You could even have chemisorption, which is when you have a chemical bond between the adhesive and the substrate. But that's a particular case. But that's one theory of adhesion. There are more. In fact, the first theory of adhesion that was proposed is the mechanical theory of adhesion, which is related to the mechanical anchoring of the adhesive at the surface. So the surface has a roughness. If you zoom this, it is even rougher at micro scale, and you can see that it's highly irregular. If the adhesive can wet this properly and penetrate into these irregularities after it hardens, then you have mechanical interlock, and this contributes, of course, also to the joint strength. But in addition to this, of course, you have an increase in surface area. A huge surface area is good also for van der Waals, to have more physical force. In general, you have a rough surface because you eliminated the weak boundary layers. In general, a rough surface allows better wetting. And finally, you have more energy dissipation because you will have a lot of plasticity here if the adhesive is ductile. So a lot of contributions here also that contribute for a higher joint strength. Not only theory of adsorption, you also have the mechanical part in most of the joints. So that's for the theory of adhesion. You have some ideas, some notion about in which conditions the substrate should be to have a good joint, a good adhesion. And this is basically related to the surface energy. This is a key point.